All right, so let's get started with today's lecture. So before that, actually, most of you should, I guess all of you should have seen an email I sent out yesterday about applying for undergrad energy scholarships. So these are scholarships given out on a quarterly basis. And it's a quick application, it's a short form to fill out. And the point of this scholarship is to award students who we think has the potential to continue in the power and energy industry. So if you look at the scholarship, it basically asks you to write a short statement about why you deserve the scholarship, with the emphasis being on, if you're given the money, how would this help you to contribute to power and energy industry? So it's quite, since this is specific to people in power energy or people who's taking power energy classes, there's a smaller pool of people compared to general scholarships in the department or in the college. And there's $2,500 for this quarter. Right? So you do want to take a look and apply. It's not that many people applying, so there's a fair chance of getting it. Right. So any question about that? Okay, so you should have seen the email, right? So you should have seen the email sent out yesterday. Okay, yeah, so I encourage you to apply. It's not all that competitive, and sort of good amount of money for a short statement and filling out some basic information. Okay, and also if you have gotten before, you're still eligible. So each round is considered a new application, and we don't really take into past, whether you have been awarded in the past into account.
Quick question for that one.
Yeah.
So yeah. The EEIC, what does that stand for? Like full word?
I'm not quite sure. It's probably something energy industry consortium. Right? So it's our external board. So we have a external board formed by local companies like Seattle City Light, Pearson Energy, Tacoma Light and Power, and so on, that advises us in the classes we offer and the material we teach in the class. For example, they'll offer advice on this class, what kind of material to teach in this class. And then from their perspective, they want to hire people, right? So local utilities are always hiring young engineers. It's actually the big thing for them is to find enough people to hire. Right? So that's why they have this scholarship to encourage people to go to the field. So if you want to apply for it, then the best thing is to talk about what you want to do in the field. Okay, any other questions about it? Right. Yeah. So do take do take some time to apply. It shouldn't take you all that long, but it's worth a shot. We generally award maybe 7 or 8 every quarter. Okay. So then continuing from last time. So last week this Monday we talked about generation and demand, right? So the whole point of the power system is to make sure generation equals to demand. So last time we talked about generation, we talked about different conventional generation, and we talked about renewables. We talked about the forecast, how the generation mix will shift in the future. And all of this shift is basically driven by demand. Okay, so power system, the way that we sort of think about the system is that demand is external and demand is not controllable. Okay, to a first approximation, we think demand is fixed. Right? So the way we think about is the mental model we have as demand is not controllable. Right? So this is very, this is still, it doesn't mean it doesn't change. It changes, from in time, but it's just not something that we can control. Right? You cannot tell customer consume, 1 kilowatt at this time. So demand is some external entity, some external variable that's not controllable. And the generation is adjusted to meet demand. Right? So and the idea is that generation has to meet demand. Right? Our expectation is no matter what the demand is, we'll have enough generation to meet it. So in this class, we'll see what demand looks like, what type from within a day, what is the typical electricity demand in a home, and then what kind of special engineering considerations this creates for us. Right? This is again quite special of a system because, for example, compared to transportation, then congestion happens all the time. And there's no guarantee you won't get from somewhere else. There's the road will be open. There's no congestion and things like that. For electricity, the expectation is once you turn, once you flip a switch, you expect electricity to be off. Right? So this is different than something like transportation. This is again different than internet. Right? Nobody guarantees you a bandwidth. Internet provider give you their best service, right? Best effort service, but it's not guaranteed. Right? But however, in power, we guarantee demand is satisfied. And that creates some sort of unique challenges for our field compared to other fields. Right? So what does demand look like? Right? So demand, there's sort of several categories of demand that behaves differently. Right? And they each is about 1/3 each. They each is about 1/3 of the total demand. So we have residential demand, we have commercial demand, and we have industrial demand. Well, let's look at residential demand. So residential means your home. Right? Well, what does the demand look like in your home? So we look at residential demand. I guess this is for sure pre-COVID. Right? So this has sort of very clear patterns, night and day patterns. Here we have the demand, right, rising around 8. So this is the morning peak. This is the evening peak. Right? So when people wake up, they consume some energy, then they leave the house. Then you have an evening peak when they come back. Right? So this is a typical, you can think of this as weekday. This is more like a weekend demand. So when people are in home, right? So you have a relatively long, sort of long peak naturally. Right? Okay. So this is for one customer, your demand may look like this. Right? So if you look at this demand, what you should notice is this is a very spiky demand. And the idea is from the max to the mean, this is a very large dynamic range. Right? Your maximum demand is much, much, much higher than your minimum demand. Okay? We have different spikes that happens in the day. But because these are very spiky and they don't last very long, that creates a situation where the maximum demand is much larger than the minimum, also much larger than the average demand. Okay, right? So this is something unique to the energy system, as you have this sort of very bursty demand, right? Very spiky demand that comes in. So this is another example you observe for another home, you observe the same thing. Is again, it's very spiky. You have a lot of spikes, but then the floor is kind of low. Okay? You have kind of low floor. So residential, the behavior for residential is, easier to categorize than say industrial customers. Industrial customers really depend on which industry you're doing. Right? So if you're doing, process industry, so what this means is, let's say your smelter and your steel foundry, then you're relatively flat. You have sort of very good idea where your demand is. You're quite flat. Compared to something like manufacturing, where your demand may be again quite spiky, or compared to something like a shipping center, and your demand is also quite spiky. It depends on when exactly the work happens. Okay, so different customers definitely have different demands. So if you look at this, let's look at the home demand, for example. Let's look at the our residential customers. So what do you think these spikes are? Like, what is this for spiky things? Like, what things in your home, consumes electricity like this? And it, right? So microwave is one, right? Microwave is one. Right? So the spikes are in general kitchen appliances. Right? So the spikes are kitchen appliances. These are very spiky, or microwave, as we said. It creates a very high draw in power, but normally doesn't last that long. Right? Well, normally it's only a few minutes. So what are these sort of low cycling things? That's around the minimum.
Fridge.
Your fridge and HVAC, right? So these are the floor things. These are HVAC. If you cycle air in your home, the fan turns on, periodically, or your fridge. Right? That have compressor that happens, once in a while. Right? And another source of spikes these are washer and dryers. Right? So they are also very spiky, right? When you're spinning, they may consume a lot of power, but then again, they're not on very long. So let's take a look at Professor Kirshen, Daniel Kirshen, actually went into his home and figured out what his demands are. Right? So he went and basically look at all the ratings of his appliance, his lighting, his computers, and so on, and figure out his demands are, these are the capacity, right? So these are the capacity or the peak demand. Okay. So his capacity in lighting is 2.5 kilowatts, kitchen is 10 kilowatts, and so on. So what you should notice is, again, our computers and television and things are actually quite low. The demand is quite low. Still, most of the time, the demand is from things that heat things up or convert things into heat and so on. If you add this up, he has about a 20 kilowatt. So this 20 kilowatt peak demand. Right? So if everything in his home is turned on at the same time, then he draws about 20 kilowatts of power. So of course, he doesn't always consume 20 kilowatt, right? So, it's still very spiky, right? So depending on when his home, then most of the time it's still quite low. You have some cycling of the HVAC or the fridge, and then you have some peaks in the evening, right? Maybe you're cooking dinner or you're washing clothes, you have some peaks. The problem with the peak So this creates a challenge where the peak load, right? So whereas your typical peak load is smaller than your installed load capacity, and then your your minimum load is much smaller than the peak also. So your home, his home, the actual capacity, right? If you want to turn everything on, is 20 kilowatts. But the peak during a typical day is nowhere near that. It's very unlikely you turn everything on. Right? They're very unlikely you turn everything on at the same time. So your peak is much lower than the 20 kilowatts. And then your average is still much, much lower than your peak. Okay, your load factor, which is your average load divided by your peak load, is only about 15%. And your capacity and your peak load is much less than your installed load capacity. So this is the nature of electric load in a residential customer. Do you see? Now let's say I'm a utility and I have to, install. I have to install the infrastructure to supply this power. Then which of this load do I look like? Do I look at the? Let's say I have to install a new transformer for this house. Then should I install a transformer that has a rating of the average load, the peak load, or the install capacity? How big a transformer should I give to this house?
The peak load.
Right. So normally, so that's the correct suggestion. As the peak load, or a little bit higher than the peak load. Right? Because you definitely do not want to target the average load. Right? Sometimes you may not be able to supply the peak. You also don't want to target the load capacity. That is too large. You're wasting money if you install a transformer of that size. So normally, as what you do is you try to estimate what the peak load is, I say throughout the year, and then multiply that by a safety factor, and install a transformer, of that size. Right? So for this house, you may install a transformer. Let's say that's 7 or 8 kilowatts, right, to give you some buffer to supply the peak load. Okay. So this is for one customer. But this is, again, a lot of inefficiency, right? Because my average load is still quite low. Right? So I'm installing a big transformer. I give you a lot of capacity, but vast majority of the time you're not using it. Right? You don't use it. Then so how do we, and we can extrapolate this from one house to entire grid, right? So if all my grid is like this, where my load factor is very small, is in the 10% range, then I'm wasting a lot of money. My infrastructure is wasting a lot of money because I'm installing for something that very rarely happens. So how do we solve this problem? Any idea? Right. So as a utility or as a system operator, you definitely do not want your install capacity to be 10 times larger than the average load. That's just not very efficient. So any ideas how we solve this?
Do like
I guess a
multiple.
question. Oh, sorry, go ahead, John.
Okay, like multiple homes share like the same capacity, so that like it's really unlikely that everyone will be like maxing out their home at the same time, so you can kind of like share that extra capacity.
Right. That's right. Exactly right. You want diversity in your load, basically. Right. This is sort of because not everybody peaks at the same time. So if people peak, at different times, then I can average this peaks out. Right. I can average all those peaks out, and maybe I can improve my load factor. Right? I can improve my efficiency. My average is closer to my peak. Right? I want my average to be closer to my peak. And the good thing is you have this sort of natural diversity, right, among people. We don't all exactly cook dinner at the same time. So this diversity definitely helps. And it's important to aggregate load. Okay? So it's important to aggregate sufficient number of loads such that this diversity effect kicks in. Otherwise, you'll be, you're very inefficient in your capital infrastructure. You become very inefficient there. Okay, so we want aggregation, we want aggregate load. This really helps us. And if you look at the aggregate load, then it's a lot better than, say, a single household. Right? So this is a typical load profile from the UK, from Great Britain. Right? But then, yeah, go ahead.
So for the aggregate load, I'm kind of confused with that.
Yeah, go ahead.
So is this like the power from the same supply? Like, oh, I was thinking of like people using like the demands like reduced because of they use the power from a different supply, like oils or other stuff, or like solar panels or something like that.
No, it's not that. It's that you want to supply many people at the same time. You want a system with large number of users. You really want to design your system with large number of users. So if you're, if you're utility, you want to deal with, entire city of Seattle. Right? So for people to aggregate out, to sort of even out the spiky behaviors. You want that.
I see.
So much easier to deal with aggregate than deal with individual. Right. So if I'm the utility and somehow I'm going to build a line, right, to each of the customers, then for each of the customers, I have to build a big transformer because I have to take care of their peak. Whereas if I aggregate the people together, right, I can do this for aggregation, then I smooth out the variation. It's much easier to deal with for a smooth out profile. So for example, if you look at the UK, then the peak, right? Let's take a summer day. Then the peak to valley is not so bad, right? It was 10x before. Now it's twice as large. So it's a lot better. It's a lot more smooth if we can aggregate people. And say, if you look at this sort of plotted, this is a more detailed graph. Then if you look at the max ratio from the maximum load to the minimum load, this is only actually 1.5x as large. Right? So this means if I build, say, the generation infrastructure, if I build a generation infrastructure, and my generations, of course, has to be able to supply the peak. But then I'm not wasting a lot of money. I'm not wasting a lot of resources because the minimum load is relatively close to the maximum load, right? So I'm not that inefficient compared to if my generator is supplying a single household. That is quite inefficient.
So how does it,
yeah,
how does it smooth out that much though? Like, I understand obviously aggregate is way better than person to person, but it's still true though that there's a spike in the morning, a spike in the afternoon, and that's generally true, especially pre-COVID. Of we'll just take this country for example. So how does it smooth out that much if there's still those, the 8 to 10 and the 6 to 8 in the evening times that are spikes?
Right. So the idea is you're not only aggregating over the residential customers, right? Or aggregating over industrial and commercial, right? So when people leave home, they're getting pre-COVID, they go to their offices. So the residential load drops, but then the commercial load kicks up. Right? So that shifts up. But then if you look at aggregate, then it's relatively flat.
Got it. That makes
a
lot more sense.
Different industries, you have, so diversity is behavior diversity, temporal diversity, different types of load. All that is helpful to smooth this thing out. Right? The smoother the curve, the better it is. So again, when we operate the system, it's not the max often that hurts us. It's the range between the max and the mean that's hard to deal with. Often we want this to be close. Right? We want the curve to be smooth. We want there to be a small dynamic range. The absolute height of this curve is not often that hard to deal with. That's a good question. Any other questions?
So in this case, you basically think about like how to supply to those like residentials, like commercial, and then like other parts, like to average the peak together to make the graph close together, the maximum and the minimum.
Yeah, so the max and mean are close together because if you have a single customer, sometimes you're not consuming energy, so your mean is really, really small, right? But here, if you aggregate all a lot of industry and residential customers together, and then someone's always consuming power, and so we are moving the two max and mean together, much closer together.
So does this mean like multiple homes share the same transformer then?
Right, so multiple homes will share the same transformer. Also, this means if I'm building generation, right? I'm not building a generator for a specific home or for a specific industry, right? I'm building a generator. I'm building a generation to supply this entire system. Right, so there's sort of the transformer and transmission line capacity being shared. There's also the generation capacity being shared.
Here's what I don't like. Kind of, I'm still kind of confused. So, example, if like one of the area is like the peak is really high, and then compared to the other areas, like the peak is like one time less, like a little bit less, and then if you do the generation, make like a system of generation, which like the peak is average. What about like those like really high peak area? Is that able to do you able to supply for that?
Right, so that's a good question. That has to do with transmission constraints, right? That's saying, do I have enough transmission line, or does my transmission line have enough capacity, right? To even out the so spatially, some place with higher load, some place with lower load. That's a good question. Also, a question we'll not talk about in this class. That requires 454. Basically, in that class we'll talk a lot more about it. But still, aggregation helps. Right? So if this picture is to say, if you ignore the transmission constraint, if you assume we can transmit electricity freely within our system, then this is the picture we'll have. Of course, you have more localized effect, and that requires sufficient transmission capacity, but still aggregation helps.
So kind of extending on that, excuse me. Say for example, the Kershaw household,
right?
He did decide he wanted to go turn everything on at once. Is
Right.
that when you trip circuit breakers? Or
oh yeah, you'll trip a circuit breaker.
So is that what those are? Because I mean,
Yeah.
that's what I was asking. Like, does it just not allow you to turn stuff on at some point? Does the breaker
you have
trip? Does it?
Yeah. Your circuit breaker will trip. You have a current limiter. It limits your current draw. So you trip if you trip your circuit breaker. Yeah, that's a protection built into your home, right? But you trip at a pretty high current. Your current nowadays, you trip at a relatively high current, but still wouldn't allow you to draw a current that will break it shouldn't allow you to draw a current that will break some devices. So you have protection.
So obviously each circuit in the house has a breaker, but then the house as a whole, as far as the system look as it has a breaker as well.
Has a breaker as well.
Yeah. Okay.
The house as whole has a breaker. Your transformer has a breaker. Right. The line has a breaker. There's many breakers going upstream. Everything has a breaker going upstream. Okay, so this is the typical low profile, right? We have this low profile. So as we said, there's a lot of benefit. Right? Benefit of aggregation. Aggregation is really useful. Aggregation is really useful. Right? The good reason, a big reason of why the grid works is because aggregation. Right? So diversity. Eliminates sort of sharp variations. Right, so if you think about the max to mean ratio for recursion, this is about 70 to 1. if we run the numbers. For UK, this is about 3 to 2. Right? So of course, 3 to 2 is much easier to deal with than something that's 70 to 1. Okay? So each customer with its own generator is not very efficient. So we always need some scale of aggregation for the system to work. And this sort of diversity effect is quite common in engineering problems. Anytime when you have resource, this sort of common resource sharing, you have diversity with help. And you can formalize this. So we don't have, we don't necessarily have the probability background to formalize this. But after you take probability or random processes, you can actually formalize the idea of diversity. You can compute exactly what the gain is by having diversity. Right? So it's quite important to have this. There's a lot, so you can do formal math on here. We're not going to do that because we don't, assume probability in this class. But to know that this is not just a sort of losing situation. There's sort of there's equations we can derive from this. Okay. Right, and the idea is, if you're building generation, you want generators to, be on at least, try to be on at the most of the time, right? If you're supplying something with max to min 70 to 1, then if you build a generator for the max, it's off vast majority of the time. And so you want a generator to operate at fairly good efficiency. Right, so we're gonna aggregate load. It's important to have some space, something that aggregates the load. So of course, when you aggregate the load, it doesn't mean the load is flat, right? This load is definitely not flat. Right? Even the aggregate over the entire UK is not a flat load. Right? So this load is impacted by many factors. Right? There are sort of factors going from time of the day. That's probably the one we're most aware of. Going to day of the week, time of the year, whether it's a holiday or not, whether it's, what the temperature is, whether we have special events, right? Whether we have special events. When we have special events, again, things are coupled together. So the, biggest, right, so sort of the common example people always give is, when Super Bowl happens in the US, as you observe very synchronous demand of things going up and down. Right, so it's sort of easy to tell how many people are watching Super Bowl just by looking at the demand, electricity demand, how that is shifting. Right? So you have this sort of, again, it's not all flat, right? It's not perfect diversity. So you have this sort of coupling behaviors. And then you can look at other, there's sort of special interesting things, right? This is an eclipse that happened on August of 1999. And then demand dropped very fast, actually. Demand dropped very, very fast when the totality happened, because everybody went to watch this. Okay, so demand dropped quite a bit, and then demand recovered. And then demand recover. So we have this sort of special events that impact demand. So the upshot is of all of this is we still need to forecast demand, right? So we said demand is not controllable, which is true. We don't control demand, but we try very hard to forecast it because you want to be able to know, for example, this will happen, right? I'll have this sort of big changes in demand. So when we forecast demand, we'll take all these things into account. Every factor here we'll take into account. We'll try to forecast the demand as accurately as possible. Okay, so demand forecasting is a big industry. Nowadays, for example, there's a lot of deep neural network being used to forecast demand. Right? As you throw all these factors into it, let's say you train a deep neural network, and you hope to get a good forecast of the demand. There's very special techniques about do that. But if you go, into industry, you may work on demand forecasting, which is, can I predict demand when it's smooth like this? And also, can I predict this kind of sharp changes in demand? So these are the short-term factors. These are, you can think of the sort of day-to-day variations in demand. And then, of course, there are longer-term effects in demand, right? Are we shifting towards more industry production? Are we shifting towards individual consumption? For global warming, are we the summer and winter peak changing? And we're starting to see this here in Seattle. Seattle was very much a winter peaking area, say a decade ago. Our demand is very high in the winter because we're heating. Our summer demand is relatively low because most places don't have air conditioning. But now we're transitioning from a winter peaking to a system that peaks both during winter and summer. So that will actually change how we think about operating the system. So this has, now you see this in the last 10 years. So you look at some demand curves in Seattle, you'll see this sort of shift in long-term trending demand. And that impacts how we think about building new generators. And then again, COVID is something that nobody knows will happen, right? Nowadays, utilities and operators have to think about what happens in the summer, right? Will people go back to offices? Will people still stay home? Is it a mixture of the two? And that has implications on what the summer demand will look like. Right? So that is something, many people are trying to figure out. But again, that's something not very easy to do. Okay? So this is, how the system will operate is you try to think about the demand is, and you try to think of, do I have enough generation to meet this demand?
So did the aggregate change that much for COVID? Because obviously I understand a lot of people, I understand a lot of people are now working from home, but obviously all that energy is now not being used in the commercial sector. So was it somewhat of an offset or was it a huge change?
It was a pretty big change. It was a pretty big change. So the way to think of how big a change it is, so normally for load forecasting, right? Let's say you're forecasting, for a city 24 hours ahead. Let's say for Seattle, we're trying to forecast, the consumption at 3 p.m. for tomorrow. Then what do you think the error is? How good are we at forecasting this kind of things? Any ideas?
15%.
No, we're much better than that. Right, give the engineer some credit for this. We're about, so if you look at a fairly big area, we're about 2-3% error. We're pretty good at it. We're very good at it. But then, so 2-3% error is what you would expect, right? So this is sort of the variation you expect. When COVID happens, this went to 15% or 15-20%, right? So it changed pretty dramatically compared to what we're having before. Right, so 15% to 3% is a five-fold increase, right? It's five-fold increase in error. So it's pretty large error for operators. It was not easy. It was not trivial to deal with. And then as we run, as we go back, right? As we have more activity, people go back to work, right? We go back to school. How this will change, we're still not sure. And there's quite a bit of research on trying to figure this out. So it's not trivial. It's not trivial trying to plan this. And the reason you have to plan about this is if you look at a generation or look at the load, right? You have to plan your generation. Right? You have to plan how you're going to generate this load, right? And the way you plan for generation is you try to match different type of generation for different type of load. Okay, so you're trying to say, hey, I have some base generation that should always run. I have something that runs, in the intermediate regime. I have something that only runs, when it's a peak. Okay. And these are some things you have to sort out. We need to have an idea of what are the base units, what are the intermediate units, how many peakers do I need. We normally need to know this well ahead of time. You don't want to be Texas this winter and be caught off guard. Right? So you want to plan this ahead, ideally years in advance. But as much as, still, if you cannot do yearly in advance, so for, as we move, to the post-COVID time, we don't know, but we still want to try to plan as much as possible. We want to plan as much as possible with this, right? So base units, right? So base generation are the things that are just on most of the time, right? Things that we don't want to turn off. Okay? We don't want to turn off. So what kind of units are base? What kind of generation are the ones you don't want to turn off? You just want to leave it on all the time. Nuclear is definitely the most important one. You really do not want to shut off a nuclear generator if it's not planned. Are there others?
Coal because of the ramp up speed.
Not really. Coal is because coal is sort of expensive, unlike nuclear. Nuclear is once you build it, the operating cost is really low. Right? So you really want to allow it on, it's really cheap. Its cost is really, really low. So coal, for many coal units, we don't have that. So but for a lot of gas units, we will actually want to run. So this is combined cycle gas. So this means gas units that does both power generation and heating. These are pretty efficient and they're important for heating purposes. So we want these to be on as a base load, as base generation. Anything else?
Hydro.
That should come. Yeah, go ahead.
Like hydropower plant, like dams.
Yeah,
not
like
hydro, not hydro, not hydro. Because dams, as we said, often needs to do other things, right? So the Columbia River, right? So we get a lot of power generation from the Columbia River on the Washington and Oregon border. The dams on that river, the number one priority is not power generation, right? It's agriculture. So it's not a base generation. It's not like nuclear. You set and forget it. Dams change all the time. So it's not really, themselves are not all that flat, the generation. Anything else? Although there are hydros that actually run all the time. So these are called the run of the river. So these are the hydro plants that does not have a dam or reservoir, right? They're basically, we just put the turbine in the river itself and there's, a lot of flow, it generates power. If not, it's not. So they're just to generate electricity. So and they cost nothing once they're built. So you definitely want these to be on once they're built. One other big category for this base generation. What else is once you build it, doesn't take any money to operate?
Solar.
Right, solar and wind, right? So solar and wind are renewables. Mostly solar and wind, right? So it doesn't, wind and solar is once you build it, again, the operating cost is almost zero. So it should be on as much as possible, should be on all the time. Right, so these are the large base generation units. So you look at intermediate generation, then these are hydro. Right, so you should use them if they're available, but for big hydro power plants, they're not always available over the entire course of the year. It depends on what else they're doing. But if they can generate power, then they're very, very cheap power generation. Right, so that's what we have. Then here you have some coal plants, right? This has been displaced by the cheap gas plants, but still, they're on, you want to use them, right? If they're there. Then if we have peaking generation, these are the generators that's only on, small amount of time, right? So they're not very efficient. They're not very efficient, but they need to ramp up and down very quickly to meet the peak. So these are the open cycle gas. So not very efficient, but something that ramps very, very fast. And then, for example, diesel generators. Again, not very efficient, pretty costly, but can ramp very quickly, can ramp in sort of the minute time scale. So these are the different type of generations we have. Any questions about this?
Oh, you mean like it's generate the power faster?
It ramps up faster. So going from 0 to max, a diesel generator can go in can ramp to max in 5 minutes. Right? Whereas if you take a nuclear plant, going from 0 to max will take you a long time. Right? So this is the ramping rate of the generator.
Sorry, go ahead, John.
Okay, what is open cycle?
Open cycle are the gas power plants. So combined cycle are the gas power plant that generates both heat and power. So we'll cover that later in the course. We'll look at sort of different type of gas generators. But combined cycles, right, you have to boil water. You have to boil water to have steam. Steam turns the turbine. Combined cycle is you have hot steam coming out. You can use this heat to do something else. Open cycle is that just gone, right? That heat is just gone. You don't use that. You only use the sort of the steam to turn the turbine. So it's less efficient than the combined cycle ones. So have any of you seen the UW power plant that's by sort of the trail, Berg Trail? That one is a combined cycle gas. It also does heating for us.
So is it true that hydro plants have virtually no storage? If they're running, they have to be feeding the grid, or is that not true?
No, if they have a reservoir, they have storage.
No, like not storage for power. Like if they wanted to run water through the plant, do they have the ability to store that energy somewhere for use later time, or when they're running the turbines to generate power, it needs to get fed into the system, is what I was always told.
Yeah. If the water is running past a turbine, then that electricity has to go somewhere into the system. Right? So they have the choice of not, storing the water in the reservoir. They have a choice of, just spilling the water without going to the turbine. So that they always have that choice. But if they want to, run water through the turbine, then that turbine spins. So that power has to go somewhere.
Right, that's what I'm asking. When they do that, is there a storage system
No,
at all? Like,
no.
or it has to go into the grid, right?
Yeah, it's as any other turbine. That current has to go somewhere. The power has to go somewhere. It has to go to the grid. And later in the class, we'll see an example of when that doesn't happen, and sort of a very bad catastrophe at a hydro generation station when that doesn't happen. Basically, the whole thing just blows up. We'll see that later in the class. Does open cycle turbine looks like a jet engine? Sort of. For the steam, but yeah, you can think of it like that. Okay, so then later, so let's take our break now. But then when we come back, so the next part of the class is to look at different kind of generation technologies. And we'll do that starting from solar, because solar looks very much like a power electronic circuit. Right? So we'll start with solar because that looks most like power electronic circuits, which we have been covering. Then we'll do wind, then we'll do conventional generation, then we'll do hydro generation. Okay. So let's take our break now. We'll come back at 3:37. We'll look at solar generation. How do we generate electricity from solar panels? So again, any homework questions, please ask now. Okay, let's get started again. So we're going to now talk about solar energy, right? How do we get electric power from the from solar energy? So the idea for solar energy, the way we're going to cover it is through two steps. The first is we want to say, let's say this is Earth, right? So want to figure out how much energy you have if you stand some point, right, at the surface of Earth. Right? How much, fundamentally, how much energy are in the photons coming to us? Then we want to understand, given a solar PV panel, how much electricity or how much current is being generated. Okay, so this is a two-step process. First, we want to figure out how much energy do we have, and how much of this can we actually turn to electric power. Right? So these are the sort of two-step process we'll have. So let's first look at how much energy do we have. Right? So fundamentally, if we stand somewhere on Earth, on the surface of Earth, how much solar energy do I have? And this basically has to do mainly with the angle, right? The sun makes to you. So this angle, this Venus angle, so this is zeta. This is a Greek letter for this is zeta. This is a Greek letter. The zeta is the angle of the center of the sun makes to the center of the Earth, to the parallel of the center of the Earth. Right? The smaller the angle means the sun is directly on top of you. And the larger the angle means the sun is sort of, more and more perpendicular to you, right? So we want this angle to be small, right? So smaller the angle, the larger the amount of energy you can have. Okay? So this is captured by equation in the following way. So the equation we can use something called solar power density, where this rho trying to measure, this has a unit of, let's say, kilowatt per meter squared. So imagine you have a 1 meter squared area. Want to know how much solar energy is on this 1 meter area square. That's what we want to know. So this depends on many factors, right? Depends on the cosine of the angle, right? So this is how close you are, or the angle you make to the sun, right? The angle you make to the center of the sun. Okay. So here, this is 0 at the equator. We're going to assume that you're directly under the sun, and this is, and the angle is much larger, if you're somewhere like Seattle. Right? If you're at Seattle, then the angle is much larger. So smaller the angle, the more direct you are, the higher the power density, higher the solar power density. Rho naught is basically the number you'll get, the power density you'll get if there was no atmosphere and the zenith angle is 0. Okay, this is the power you'll get if you directly, you're 0 degrees with respect to the sun and there's no atmosphere, there's nothing absorbing sunlight and things like that. This is the max power you'll get. And this has a value of 1.353 kilowatt per meter squared. So this puts an absolute upper bound on the solar power density, right? There's nothing that can extract more power than this rho naught number. This is all the power we get at Earth. This is a number that only depends on the distance we are away from the sun. Okay? So this is, this is the upper limit of the power we can get per meter squared. And then the rest are sort of the factors that reduces the energy you get, right? Either because you're making a large angle or you have atmosphere absorbing the sunlight. Right? So if somebody try to sell you a product that can extract more than 1.35 kilowatt per meter square of power from the sun, that's just not possible. Okay? This is as much as we can possibly get. Right? So then that's a ballpark estimate. Is this a big number or a small number? Is this large or small? Right. So this is the most we can get. So should we bother, extracting this power?
Yeah, it's pretty large.
Right, so this is actually a very large number. This is a not insignificant amount of power, right? So a meter squared is not that large. Right? So a typical rooftop of a home is much larger than a meter square. So this is, right, if we can get anywhere close to this roll down number, it will be worthwhile, right? So this, we should be happy with this number. It's not a small number for us. Okay. And then the rest of the coefficients in this equation basically talks about the atmosphere effect, right? Talks about atmosphere effect. So what this, there's a lot of detailed calculation you can do here, but the way we're gonna think of is fairly simple. Okay. So alpha dt, this is the direct sort of transmittance. This is the amount of power you get without water that is not absorbed by water. Okay, so this is right without water. You have to subtract off this beta term because this is the impact of having water in the atmosphere, i.e. clouds. Right, so this is, because you have water, you have to subtract this off. This blocks some of the sunlight from getting to us. And then this alpha p is another factor accounting for sort of how much power is getting to us. So you can imagine, whether we have, say, dust in the air, whether we have other things that may block it. So these are the three things that account for the atmosphere factors. Okay, so rho naught is absolute number we can, sort of the upper limit we can get. Cosine beta is the angle. Then the other things depends on exactly where you are and the atmosphere condition, right? Whether it's a cloudy day or a sunny day. Okay, so these are summarized now in the here. You don't have to remember their names. So when we do a homework problem or typical problem will tell you, what the alpha parameters are and what's the beta parameter. So you don't have to look this up. We'll give you in the question. But it's good to know sort of what impacts the final row you'll get. Right? You're basically taking rho naught and chopping part of it off, right? You start shaving part of it off and see how much of this for 1.35 kilowatt per meter square is left over.
So
questions? Yeah, go ahead.
Yeah, sorry. How come time of year doesn't matter? Because obviously the Earth's orbit's not a perfect circle, so distance from the sun doesn't play a factor really.
It's very small, very, very small. The angle matters a lot more. The angle matters a lot more than the fact that it's not a circle. So we'll change, 1.35 by a very small percentage, but it impacts the cosine term by a lot more. So that's where seasonality gets accounted for. Any other questions? Yeah, go ahead.
Yeah, that water value is more
Yeah.
so like clouds, not humidity.
Yeah, so it's the fact that you have water, yeah, you have clouds, yes. So see, as winter in Seattle, you have a very large beta value. Other questions on this? Right, so all of these things are pretty easy to measure actually. The good thing about this equation is the angle we can compute explicitly. That's where we can compute that. And the alpha beta terms we know because from they're easy to measure, their atmosphere values. So you can plot the amount of solar radiation, solar energy in the US. And so not surprisingly, we're here, not super great. This depends on where you are. Right? Okay. So this us up, we pretty much expect this. So the sun belt, you definitely get a lot of solar energy. We don't get as much, but still even this much is not too bad. It's not too bad. Right? So you may not see the legend here, but what we get is we're roughly around here. So for us, we're about 2.5 kilowatt hour per day. Or 2.5 kilowatt hour per day per square feet, right? Per meter square, per meter square. So over a meter square of area, for a day, we get about 2.5 kilowatt hours, right? So not, as large as Arizona, but still not a small number. If you have if your roof is 10 meters square, right? So you can potentially extract, right? 25 kilowatt hours a day. That's more than enough for a single, right? For a family sometimes. Right? So this depends on how efficient your PV panel is, but still, even for Seattle, it does make sense. It's not that small of a number. Right? And this chart is sort of per year, right? This is an annual chart. So of course, winter will have less, summer will have more. But on the average, even for 2.5 kilowatt hours per day per meter square, it makes sense to build solar. It's sort of cheap enough now to build solar for this number. Right. And of course, in Arizona, then makes even more economic sense to use solar. Right. So then this is the right. So if we're talking about hours, energy per day, for solar, it's important to talk about daily energy variation because obviously we don't get the same amount of power, right, at every hour of the day. Right? There's clear day-night variations for solar. Right? So again, if you plot, this is right. So we plot time. This is say from 0 to 24 hours of a day. Obviously, a lot of times of the day you don't get anything. Right? We don't get any power. During the middle of the day, we tend to get more power. So here we'll make a very simple assumption. It will make a very simple assumption. We'll assume we have some T naught, and the power peaks around this T naught, and then sort of decays as we move away from T naught. Right? Then decays move around from T naught. So this is, we can think of this as a, you get 100% of the peak power of the day. Then as you move away from the middle of the day, the amount of power you get decays. So we need some way to capture a curve like this, right? We need to capture the time of the day effect on solar power. So the way we capture time of the day effect is we'll assume a fairly easy Gaussian. We'll assume this is roughly Gaussian. So if you never heard of what a Gaussian curve is, it's just a pretty simple curve. So rho as a function of t is a maximum you get during the day, and will decay exponentially away from it. Okay. The idea here is t naught. Here, this is your, this is time at rho max. This is the maximum power. This is the time you get the maximum power. So for example, nu at the equator, sigma squared, sigma is a standard deviation. Okay, so as you move away from, let's say, nu, you get less and less power, right? And it decays pretty quickly depending on the value of sigma. So if you have seen this before, you recognize this as the Gaussian bell curve. If you haven't seen this before, just remember this equation. Right? All this trying to do is capture the fact that solar decays. Any questions for this equation? Okay, so obviously this is not what actually happens during the day. We have clock towers, the actual power is, so in practice, what you measure is not something like this, but more of, something like this. Right? This is a much more practical trace you'll see, but we don't have enough technical sort of tools to deal with this sort of very practical traces for solar yet. We don't have enough probability and statistics to deal with this. So for now, we're gonna assume it's a very nice bell shape, and the only thing it depends on is the time of the day, as controlled by this value sigma square. All right, so if you're interested in more of, how do you deal with this actual variations, right? The actual up and down you see in practice, that's something we're covering for 51. It's how to more probabilistically think about solar generation. Whereas, so in this class, again, we care more about, the density you can get or the way that a solar PV actually works. We're not dealing with the fact that there's a lot of uncertainty with solar generation. And that's something we're much closer to research, and that's covering for 51. It's also some things where we all do actually in our own research. That's how do we deal with this kind of uncertainty. All right, so then if you look at okay, so this is a day-to-day variation, right? So for solar power, we both have the day of time variation as well as depending on where you are, right? This efficiency. So the solar efficiency is basically the density you have divided by the maximum power we can get. So roughly this is around 5 to 70%. Right? With us much closer to the 5% range, with say Southern California or Texas much closer to the 70% range. Right. So this is the sort of ballpark idea of the number. Right. This doesn't mean again your solar PV will convert all of this to electric power. This is just the power we have. Right. Later we'll look at how much of these you can actually convert to electrical power. Okay? You're not going to get all of this, but you get part of this. Okay, so let's do an example of what these numbers are. Right? So one example, this is a very typical question is, we have an area located near the equator that has the following parameter. So we'll give you all this parameter. This is a fairly dry area and not much cloud cover. And we're going to assume the standard deviation is 3.5 hours. We want to compute the solar power density and the solar efficiency at 3 p.m. At 3 p.m. So this is a very typical question you see. Okay. And the way to do this question is to basically figure out what rho max is, then plug in time of the day to figure out where rho is. Right? So the idea is you look at this equation. Right? We want to figure out where rho max is. Then we want to look at this exponential decay term and figure out what the actual rho is for this problem. All right, so let's solve. So I knew we have rho max. Right? So this is a point in the equator. So the maximum solar power density during the day happens at noon. So we want to compute rho max, and rho max is rho naught cosine theta alpha dt minus beta of the water absorption times the aerosol transmission alpha p. So what's the angle here for equator?
0.
0, right? It's equator, so it's directly under the sun. So this is rho naught cosine of 0. You plug in the numbers 0.8 minus 0.02 times 0.95. We get this exactly turns out to 1 kilowatt per meter squared. Right. So then of course, at 3 p.m., we use rho as rho max exponential e to the t minus t0 squared over 2 sigma squared. You plug all this in, 1 times e to the minus, let's say, 15 minus 12. We're going to use the 24-hour standard. So we're 3 hours away from the maximum. 2 times 3.5 squared. This works out to be 0.693 kilowatt per meter squared. Then our efficiency is, right? So this is rho naught. Then our efficiency is 51.2%. Right? So at 3 p.m., we're getting about half of the maximum solar density we could get. Questions with this example? Right, and so this is a good example is because, right, so this question assumes you know two things, right? You know the maximum T naught is unknown, and you know the angle is 0. Okay, so this is often assumed in the question that you know this. Okay, so when you have a question like this, for example, on the homework, and you think you don't have enough information, right? You think you don't know the angle or you don't know the maximum time, you don't know sort of when the maximum solar density happens, then read the question carefully. Right? Often the question is say for equator. Now assume that you know the angle is 0 and T0 is at noon. Okay. All right, so this is our calculation for the density. And then there's two ways to convert the solar energy, right? There are two ways to convert this solar energy to say electricity or to something that can generate electricity. Right? So there's a passive solar system or active solar system. So passive solar really just means that we're not using a solar PV. Passive means we're basically heating something up. The passive solar means, right, for example, this is a very simple example, you heat water up. Okay? You run water through a collector and you heat water up, and this hot water creates a heat engine with respect to the cold water coming in, and you can generate power this way. This is a sort of a very simple conceptual passive solar system. This is pretty often used if all you need is really hot water. So if you really, if at the end of the day you want hot water, this is not a bad way to heat up water. It's not a bad way. Of course, we also have this sort of combined system. We have this concentrated solar, is where you reflect, you have a bunch of mirror system, you reflect sunlight, you concentrate sunlight somewhere, and you create heat that way. Okay, so this is another way to the so-called passive, as you're not actually generating any current or voltage. You're basically just reflecting sunlight and heating something up. This can still be pretty efficient, right? This can still be pretty efficient if you have enough sunlight. If you can collect enough sunlight to create high enough heat, this can work. And this sometimes is more efficient than a solar PV panel. But what this really requires sort of big land area. Right? You need something like this or something like this to just heat things up. Yeah, you need a lot of area to do this. Right? So this, we're not going to say too much about passive solar because there's not much to say. It's really not a electrical circuit problem, right? So what we'll do is next class, we'll look at active solar. We'll look at how do you generate solar current, how do you do photovoltaics? How do you look at solar PV as a circuit, and how do we think about that? Okay. So let's stop here today. Then next week, we'll finish active solar systems, solar PVs. How much current and voltage they will generate when we have a PV cell. Right? Yeah. So again, homework is due tomorrow night. And then next week, we'll start with solar PVs. After that, we'll move into wind generation and other generation technologies.